Well, my dear participants, now I am in the continuation of my earlier lecture. I am going to talk about fitting of linear, quadratic, exponential log model. See, the iron slog data available with the package dog. Dog is a package, that is, dog stands for data analysis and graphics. Uh, a package, a very famous package, is it contains a data frame iron slags which has 53 rows and 2 columns on measurements of iron contents obtained from iron slags by using two methods, chemical and magnetic. A scatter plot of the data suggests that chemical and magnetic variables are positively correlated, but the relation may not be linear. From the plot, it appears that quadratic polynomial or possibly an exponential or logarithmic model might fit the data better than a line. Thus, proposed methods for y magnetic measurements versus x chemical measurements are M1, this is the model 1, M1 model 1, this is linear model. Then M2 quadratic model, y is equal to quadratic beta naught plus beta 1 x plus beta 2 x square plus e. Then M3 exponential, it is log of y is equal to log of beta naught plus beta 1 x plus error, and this implies y is equal to beta naught into e raised power beta 1 x plus e raised power error. These models are common among the econometricians. M4 log model, it is log of y. Here we have only log of y, not log of x, but here we have log of y as well as log of x. So that's why it is known as log model. Implies y is equal to e raised power beta naught x raised power beta 1 e raised power error. The iron slug data dog package contains iron slug data frame which can be obtained as, see, library dog data iron slag require nit r. ठीक है, actually there is a package nit r which we will discuss for documentation, and we will discuss about these things. So library dog, we have to load the library. First we have to install the library, then we have to load the library, and then data iron slag, we have to load the data iron slag, we have to give this command, then require nit r cable header part of the iron slag caption is equal to iron slag data on two measurements. We need these things when we need documentation. So it brings this kind of table. So here actually it gives a lot of commands in fitting. See, OPAR stands for, it partitions the whole screen into 4 parts, 2 rows and 2 columns, 4 screen into 2 parts. Then x is equal to 6, 10 and from is equal to 10 and 2 is equal to 40 and the length is 0.11. So it will generate a sequence because minimum observations in the magnetic measurement is 10 and maximum is 40. So we are dividing this length to through equal distance of 0.1, 10.1. See, just I would go to the command line. Exercises: fit the data set trees using SLR and MLR and compare your results with M1. Suppose if we compare, see summary of results, summary of results, summary of M1, this is the result. And if we use SLR, y is equal to trees dollar volume, comma, x is equal to trees dollar girth. So if we give this, we get this result. See, just compare the results. Estimate of regression coefficient is minus 36.94, minus 36.943. Standard error is 3.36, 3.36. T value is minus 10.97. There also T value. So both the results are equivalent. Both the results are equivalent. Both are giving the same results. Similarly, if we want to compare M2, summary M2, so this is the result of MLR. This is the result of using LM. Now, if we compare with MLR, see y is equal to trees dollar volume, comma, x1 is equal to trees dollar girth, comma, x2 is equal to trees dollar height. So if we are giving these arguments, we are getting the results. Now see again, the intercept is minus 57.9877, here also 988, and SC beta is 8.63, there SC beta 8.6382. So, and p values are same. P values also they are same. So that means MLR is equally good as LM method. And then fitting the same data using SLR and MLR as the centered form and compare your results with that. So to make use of MLR, what we have to do, say for example, SLR trees dollar volume, comma, x1 is equal to trees dollar girth minus mean trees dollar girth. So this way we will get the same results. Oh. Trees dollar girth argument x1 trees dollar. Just we can check this. X1 is equal to trees dollar girth minus mean 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 trees dollar girth. So x1 is centered form of x1 is computed. Now we can fit x1 is equal to x1. x1 is equal to x1 and SLR trees volume y is equal to x is equal to x1. It is because arcs of SLR are nothing but x and y. So we have to give y is equal to t is this and x is equal to x1 and we will get the result. Similarly, we can use MLR to get the results. MLR, say x1 we have already defined. Now we have to define x2 is equal to trees dollar height minus mean of trees dollar height. So trees. So now we can make use of MLR y is equal to trees dollar volume comma x1 is equal to x1 comma x2 is equal to x2 and we will get the result. So these are the results which we can get from the transformation also. So these are the solution to the exercises. Model diagnostics, we have already talked about model diagnostics. Now I am going to talk about the three forms of the model, fitting the models for our data. See what we are doing. We are fitting first O par is equal to par MF rho 2 by 2. So it will divide the screen into 2 rows and 2 columns. And then x is equal to sequence C, x is equal to control 2. See, this is a sequence because minimum of iron slag and dollar magnetic, minimum is 10 and maximum is maximum is 40. So the data minimum of the magnetic becomes 10 and maximum becomes 40. So we are dividing from 10 to 40 into a step of 0.1 and that's why we are giving this argument x is equal to sec C from 10 minimum to 40 and step is by 0.1. And if we look into what is the length of this x, so we can get length of, it is 301 observations, 301 points we are generating. Now control 1, we are fitting the model M1. See, it is simple linear regression model. simple linear regression model, and then we are using, actually we have to run this whole, then we are getting a plot, and then y hat, and then we are adding a line. So we have to run the whole chunk and then see. This is the linear part, this is the quadratic fitting, and this is the exponential fitting, and this is the log fitting. So to understand these things, we have to go to the PDF. See how we are fitting these. We are generating x is equal to sequence this, then we are fitting MLM, simple linear regression model. We are plotting, it will generate a new plot, that is scatter plot from magnetic versus chemical, and then plotting character is 16. Then y hat, these are the predicted values, m1 coefficient 1 plus m1 coefficient 2 into x. So it is the predicted value of y hat, and then line will add a line on the same plot, and that is x, and here on x-axis it is x, and y-axis y hat, and LWD is equal to 2. So this will generate this plot. These are the observed values, and these are the y hat. Values. So these are the observed values, and these are y hat values, and this is the line fitted. So this is linear. And then we are fitting another model, and that is quadratic model. See, quadratic model is somewhat like this. Simple linear regression model is equal to beta naught plus beta 1 x plus error, whereas quadratic model is y is equal to beta naught plus beta 1 x plus beta 2 x square plus error. So this is quadratic model. So here the form x square is being involved. So what we do, we write this model as not as y is equal to beta y tilde as x1 plus x square, because here x square in the formula arguments also these operators work. So first we will insulate. So it will be lm y tilde x plus insulate x square, and then we will use data is equal to iron slag, whatever. So we have made this formula here in fitting of quadratic regression model. It is magnetic versus chemical plus chemical, that is x, plus I, we are insulating chemical, so that first it will square each element of chemical, and then it will be a part of the model, and data is equal to iron slag. And then we will plot will generate a new plot, magnetic versus chemical, data is equal to iron slag, main is equal to, the main title is quadratic fit, plotting character is 16. So y hat 2, m2 coefficient, this is the beta naught, then plus m2 coefficient 2, this is the beta 1 into x plus beta 2, and that is coefficient 3 into x square, and lines will add a line in the plot x versus y hat 2, LWD is equal to 2. So this will generate this plot. This is the quadratic plot. This plot will be generated, and see, it fits better. It fits somewhat better than the linear. And then we are going to talk about M3 in which log of magnetic versus chemical. So data is equal to iron slag, and plot magnetic versus chemical, then same scatter diagram, then log y hat 3 is equal to M2 coefficient 1 plus M2 coefficient 2, and then it is x, and then y3 y hat 3 is equal to exponential log of y hat. So it will give the result. Then lines, so it will generate this plot. It will generate this plot exponential, and then log 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 M4 log of this versus log of chemical, data is equal to iron slag, plot log of magnetic versus log of chemical, data is equal to main is equal to log log, data is equal to iron slag, plotting character is 16, log hat 4 is equal to M1 M4 coefficient 1 plus M4 coefficient 2 into log of x, and then lines log of x versus log y hat LWD is equal to 2. So this will generate this fourth plot, log log model, log of, this is the log log model. So then to go to the original settings, we have to put the command par o par, go to the original settings, so that this screen which we have divided into, this is the par o par, in which we have divided the screen 2 columns and 2 rows to fit those 4 graphs. Now it should go to the original setting, that is 1 by 1. So that is all. Now see, it is a different issue that which model fits best. From the graphics, it seems that quadratic model fits best. However, this is a totally subjective on the basis of graphics. There are standard objective methods to compare these different models, and these issues will be discussed at somewhere else. But see, if you go into see, this is the M1 M2, say M1, see, print M1. M1 is simple linear regression model, whereas print M2 this is the quadratic regression model. If we have seen the graph that quadratic model fits better, it is evident from this graph that quadratic model fits better than the linear regression. But there is a criteria that is known as model selection criteria, Akaike information criteria. AIC is the implementation of that. Now see, AIC of M1 is what? It is 309, whereas AIC of M2 is 304. So from 309 to 304, it is a difference of around 5. It is a difference of 5. So 5 is a significant improvement. So there is significant improvement in the quadratic model as compared to the linear regression model. But actually this example I have taken from a book by Maria Rizzo, published by Springer, and that the title of the book is Statistical Computing with R. So she has discussed this problem there, but in a different scenario, and she talks about the cross validation technique. So if we will make use of cross validation technique, we will find that the minimum comes criteria for model selection, minimum comes with the quadratic model. So quadratic model is the best model among these four. But I am not going to discuss those things, cross validation and other things. So now I shall talk about another concept, and that is known as generalized linear model. See, generalized linear model. Generalized linear model actually here I have not given anything regarding generalized linear model. Generalized linear model is nothing but it is a kind of the first thing which was introduced was GLM, and GLM is y is equal to x beta plus e. But there are certain problems with GLM. That means it has to meet the assumption of ANOVA, and that is normality assumption, homogeneity of variance assumption, etc. Homogeneity of variance, etc. So Box and Cox, they suggested in 1964, Box and Cox, they suggested a transformation of the data, and that is known as Box-Cox transformation, and that is very famous paper due to Box and Cox. And they suggested that certain power transformation, y raised power lambda minus 1 by lambda. So for different choice of lambda, say for example, if lambda is equal to 1, there is no need of transformation. If lambda is equal to 0.5, that means square root transformation. If lambda is approaching to 0, so that means logarithmic transformation. So they suggested certain Box and Cox transformation, and people enjoyed with this Box and Cox transformation. But still, any transformation does not satisfying all the needs, and moreover, transformed data, transformation of the response creates a problem in interpretation. So Nelder and Wedderburn in 1972, they presented a paper in Royal Statistical Society, and they gave the concept of GLIM, generalized linear model. So generalization, this is a generalization of linear models. Generally, this is known as GLM, and this is known as GLIM. So they suggested that in GLIM, it is a generalization. Say for example, normality error follows normal distribution. But here in GLIM, error follows a member of exponential family of sufficient statistics. And then they gave the concept of link function, and these two things are very important. So family and link function, say for example, if you talk of probit model. So probit model, if you express probit model in the form of, say for example, p raised power x 1 minus p raised power 1 minus x, and this is the fx of Bernoulli random variable. So if you use a raised power x is equal to x, a raised power x is equal to e raised power x log of a. So if we make use of this result, it is fx is equal to a raised power x, it will be e raised power x into log of p and into e raised power 1 minus x into log of 1 minus p. So ultimately it becomes x into log of p upon 1 minus p. If we solve this, it becomes, so here it is a member of the exponential family of sufficient statistics, and here summation xi is sufficient statistics for p, and this log of p upon 1 minus p is termed as logit link function. This is known as logit link function. Logit link function. So we can fit here logit link. Similarly, in the case of Poisson distribution, it is logarithmic link function which is being fitted. So here data is equal to insect spray, and the function for fitting this GLIM is in R. Here LM is meant for fitting this GLM, but for GLIM the function is GLM, and its arguments are formula, and additional arguments are actually here link function and family. So data is equal to insect spray. We have already discussed insect spray data. See, this is the nature of the data, counts and spray. So we have fitted M1 is equal to GLM, count versus spray, and data is equal to insect spray. Since we have not specified any family here, we have not specified, otherwise it should have written like this: GLM count is modeled as a function of spray, and then family is equal to Gaussian, and link is equal to identity. And then data is equal to insect spray. So this way, similarly, if we fit the Poisson regression model, because data in the form of counts, so here data is equal to insect spray, count versus sprays, and family is equal to Poisson. And link is actually here family is equal to Poisson, 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 and here default link is not mentioned. So here link is logarithmic link is being fitted. So this is the logarithmic link. Actually, if we talk of fx is equal to e raised power minus lambda raised power x upon factorial x, if we convert this into exponential family, it is lambda raised power x is equal to e raised power x log of lambda into some function, these functions. So, and in this situation, summation xi becomes sufficient for lambda, and link function is log link. So that means log of lambda is equal to x beta or beta naught plus beta 1. I should write somewhere here log of lambda is equal to beta naught plus beta 1 into x. So this is the logarithmic link function, and this means lambda is equal to e raised power this beta naught plus beta 1 x. So that way here the restriction of lambda greater than 0 is being satisfied. if we direct write lambda is equal to, if we direct write lambda is equal to beta naught plus beta 1 x, then in that situation, because the range of beta naught and beta 1 is minus infinity to plus infinity, so that means this does not satisfy the condition of lambda greater than 0. So that's why this introduction of link function is must, and that is why we have given these results. So the function is GLM, and these are the results. These are the results. Here AIC M1 is the Gaussian model and M2 is the Poisson model. Here AIC of M1 is 408, whereas in that of when we use Poisson regression model, it is 376. So there is a large reduction in the AIC value of Poisson regression model. So that's why Poisson fits much better than the Gaussian for this data. So similarly, we can talk of logistic regression model for binary data. Here we have taken this data WCGS from Faraway package and Julian Faraway. There is a great book by Julian Faraway, that is linear models with R, and here we again use GLM and we have got the results. And these are the interpretations. So I think I have completed to some extent linear models and generalized linear models. My next talk will be about nonlinear regression models. Generalized linear regression models are always preferred in the market because family of sufficient statistics includes Poisson regression, it includes normal, Poisson regression, gamma, and then binomial, Bernoulli, negative binomial. So all sorts of data, whether discrete or continuous, they can be fitted into GLM, and that's why GLM has the great preference over LM. So that's all for today.